Hi y'all, it's Miss Barker and today we're going to talk about vectors. So some quick objectives. Today we are going to define and give examples of vector and scalar quantities. We are going to analyze and describe position and movement in 2 dimensions. We are going to be able to organize and evaluate position and displacement in 2 dimensions. Here are the vocab terms that we'll be talking about today, so watch out for these as we go through our presentation: vector, scalar, magnitude, and coordinates. And this is the primary equation we're going to look at today. So this is an equation that explains the final position based on initial position and displacement. So first up, what is a vector? Well, last video we talked about how all measurements need 2 things. They need a value and a unit. Some measurements actually need a third thing. They need a direction. So for example, we have things like velocity or force or displacement. We need to know which direction that value is moving in. On the other hand, we have scalars. So scalar quantities are quantities that do not require direction. These are things like mass or temperature or distance. We can stick to just a value and a unit. So position is a vector. If we have a 2D surface, we need 2 values to help us determine the position because direction matters. So if I told you from this starting point, I want you to stand 5 kilometers away, you could do that in a number of different ways, right? You would probably ask, well, which direction? Do you want me to go 5 kilometers north? Do you want me 5 kilometers east? Where am I supposed to go? That's why every position coordinate is written with an x and a y value. All of these values are related to the origin. So they are relative to the origin, and that's just 0, 0. If we look at our point here, its coordinates are 4, 3, because it is 4 spaces to the east and 3 spaces north. If we had moved in the other direction, so if we had gone 4 to the left and 3 down, that would be -4, -3. So here we have an example of that. We're starting from the origin. We're going to go 1 space to the left or to the west. So that's going to be -1. Then we are going to go up or to the north 3 spaces. So our coordinate should be -1, 3. So again, to reiterate that, negative numbers tell you which side of the origin the position is located on. Generally, we are going to treat things as going up and right as positive, and things going down and to the left as negative. So now we can start to talk about displacement. So not only do we have a starting position, but if we have any movement, then we have displacement. So you can actually explore this a little further if you go to your online textbook, page 77. There's a little button down here that will allow you to play around with a simulation so that you can actually practice typing in different displacements and watching those position graphs change. So we can actually calculate displacement, and we can do that again using this formula, xf equals xi plus d. So here, xf is final position, xi is initial position, wherever you started, and d is displacement. Now it's important to note we actually do need to break this equation down further. So if we look over here, we have 2 equations. We have one with dx and one with dy. So we are looking at displacement in the x direction versus displacement in the y direction. So if we translate this into a sentence for our first equation, we have the final x coordinate, so our final position in the x direction is the initial x coordinate plus the x values of any displacements. Similarly for y, the final y coordinate is the initial y coordinate plus the y values of any displacements. So let's look at an example of that. So we have a robot. He's starting at 0, 0, and he's going to go 5 meters to the right, then 3 meters up, and then -4, -1. So we can graph this out like we've just done here to figure out what our final position should be, and we can double check that using our equation. So our x final should be equal to our x initial plus displacement in the x direction. So x initial is 0, plus we have +5, then 0, then -4. So we are going to add 5, add 0, subtract 4. So our final x position should be 1 higher, +1, from where we started. We can do the same thing for y. So y final equals y initial plus displacement in the y direction. Initially y is also 0. Then we have +0 plus 3 minus 1. So y final should equal 2. This means our final coordinates should be 1, 2. And again, we can double check this on the graph, and they are 1, 2. Again, just confirmation that our final position is 1, 2. So here again are those two ways that we just demonstrated on the last slide. We have both numerical addition. This is using our formula for displacement. And this is going to be the most accurate method of determining final position. We also can verify that using graphical addition. So this is called the head to tail or tip to tail method. And that just means that you are going to draw each vector starting from the tip of one to the next one until we reach a final position. Again, both of these values, both of these methods should give you the same result. So if they don't, if you try your numerical addition and then you graph it out and you don't get the same answer, there's a problem. You need to go back and check your work. Okay, let's kind of quiz ourselves real quick. So take a second, pause here. For each of the following variables, determine if they are vector or scalar. So again, just a refresher, vector values need direction. Scalar values do not need direction. Did you get them? So temperature is scalar, vector, or force is a vector, displacement is a vector, length is a scalar, velocity is a vector, time is a scalar. And all of the variables we're going to use in this course fall into one of those two categories. They can all be categorized as either vector or scalar. Okay, here's another one to pause and check yourself on. So a boat travels 5 kilometers east, 8 kilometers north, and then 8 kilometers west. What are the boat's displacement vectors? What is the final position of the boat? What distance has the boat traveled? And what vector will bring the boat back home? Go ahead and pause now. So here we have the boat's displacement vectors. We have 5 kilometers east, 8 kilometers north, and 8 kilometers west. The final position of the boat is going to be -3, 8 kilometers. So the distance is added from each displacement. So therefore our total distance is going to be 21 kilometers. So again, that's just 5 plus 8 plus 8. And then to bring the boat back to 0, 0, we are going to look at what our final position was, and we just need the opposite of that. So our final, or our vector that would bring our boat home, is going to be 3, -8.